Okay, so today we are going to look at the connection between the j function and almost integers of the form e to the pi times square root of some positive integer n. So what has been written on the screen is actually false, but it is only just so, because e to the pi times square root of 163 is extremely close to being a positive integer. It is only very slightly smaller than 1. And we may now wonder whether this strange phenomenon is but an isolated lucky coincidence, or whether something quite deep is going on behind the scenes. And there are certain other values which you can replace under the square root sign to produce an almost integer, like 43 and 67. But there's another weird thing. So if you look just before the decimal point, there is this suspicious common string of 743. And by now we strongly suspect that something deep must be going on. And it is actually the case. But let's just note one more thing. If you were to replace this 743 by 000, or if you were to just eliminate it for that matter, the integer just before the decimal point becomes an actual cube. So in the first case, it's 640320 cubed. So this 640320 is going to reappear later, so you can remember it if you want. And similarly, in the other two cases, when you take away the 743, you produce perfect cubes for the integers just before the decimal point. So now we have a lot of questions on our minds. So why are things behaving so strangely? What is 743? Why are the cubes acting like that? And why are the e to the pi times square root of 163, 43, and 67, why are they so close to being a positive integer? And it is not at all clear how we are going to explain these observations, but we know that at the end we want something like, we want to show that an integer is equal to e to the pi times square root of n minus 744 plus some really small positive quantity, at least for n equals 43, 67, and 163. But we also want to figure out whether there are other positive integer values of n, which will produce an almost integer. And we also want to know whether we can make this almost integer as close as possible to an integer. And it turns out that to answer these questions, we need to turn to a function called the j function. So at the moment, we are not actually giving a definition for the j function. We are just showing a few terms in the Fourier expansion of the j function. So here tau is a complex number in the upper half plane, and q is equal to e to the 2 pi I tau. So it turns out that every coefficient of the j function encloses some really deep information, but we are not going in that direction in this presentation. We will be focusing mostly on the 744 to explain the observations which we made earlier about almost integers. And there is an evaluation which is going to help us explain why e to the pi times square root of 163 is close to an integer. And if the evaluation is that at minus 1 plus I root of 163 over 2, j evaluates to minus a perfect cube. And this cube is 640320 cubed. And you will remember that 640320 appeared before. So let's see how we are going to make use of this fact to explain why e to the pi times square root of 163 is close to being an integer. So here's the expansion for j. Here's the evaluation which we just saw. So here tau is equal to minus 1 plus root of minus 163 over 2. And therefore q is equal to e to the 2 pi I tau, which makes it equal to minus e to the minus pi root 163. When we substitute q in the Fourier expansion for j, these evaluations give us minus 640320 cubed is equal to minus e to the pi times square root of 163 plus 744 minus all those terms. And we are going to multiply both sides by minus 1 to obtain these, to get the equation in this form, but we are going to group these last terms together because it turns out that they evaluate together to some really small positive quantity. And the reason for this is because, well, if you denote the coefficient of the j function by c of n, then c of n satisfies, so it is asymptotically equal to this expression as n goes to infinity. And this expression may look quite similar to the asymptotics for the partition function obtained by Hardy and Ramanujan. But anyway, this means that the e to the minus pi root of 163, so the powers of that, they are extremely tiny and they are able to overcome the rate of growth of the coefficient c of n, and this makes the terms in bracket evaluate to a really small positive integer epsilon. And that shows why e to the pi times root of 163 should be so close to being a positive integer. And we can very similarly show that e to the pi times root 43 is extremely close to being a positive integer because we have a similar evaluation at minus 1 plus root of minus 43 over 2. And the same is true for 67, where we have a similar evaluation, explaining why e to the pi times root 67 is extremely close to a positive integer. And there are certain questions which now arise. For example, what exactly is this function j? And when does it evaluate to an integer? And whether we can make e to the pi times square root of n arbitrarily close to an integer. And this is the definition of the j function. It is an extremely weird definition at first sight. So, just for notation, sigma 3 of n is the sum of the cubes of the divisors of n, and for example, sigma 3 of 6 is equal to 252 because 1, 2, 3, and 6 are exactly the divisors of 6. So, okay, so that's the numerator of the j function, and we cubed it as if it was not complicated enough, and then we divided by this fancy product raised to the power of 24. And so this definition at the moment looks really contrived and artificial, but the j function actually arises very naturally, as we will see later. But for now, let's just note that j evaluates to an integer if the binary quadratic form ax squared plus bxy plus cy squared is primitive, is positive definite, and has a discriminant with class number 1. So we are going to explain these terms later on. So we can note just for now that primitive means that A, B, and C have no greater common divisor than 1. Positive definite means that the quadratic form represents only non-negative integers, and it is 0 exactly when x and y are both 0. The discriminant, we require the discriminant will be negative if the quadratic form is positive definite. And later on, we are going to show, to explain what the class number is. But let's just note for now that when these conditions are met, the j function evaluated at minus b plus the root of the discriminant over 2a is an integer. And of course, that's quite surprising. And for example, x squared plus xy plus 41y squared is a primitive positive definite binary quadratic form, and it has the discriminant, minus 163 has class number 1, and this means that j of minus 1 plus root of minus 163 over 2 is an integer, as we have indeed mentioned before. It's equal to minus 640,320 cubed. All right, and we may now be wondering whether we can get infinitely many evaluations like that, making e to the pi times square root of n arbitrarily close to an integer. And it turns out not to be the case, at least not by this method, because what Baker-Stark and Heegner essentially showed is that there are finitely many negative discriminants with class number 1, although the Baker-Stark-Heegner theorem is more usually stated in terms of quadratic fields rather than binary quadratic forms, but that's that's essentially the result. And this makes 43, 67, and 163 really special, particularly 163 because it makes e to the pi times root of 163 surprisingly close to being an integer. So we are going to look first at the first question. What is the j function and how does it arise? It arises naturally from elliptic function theory, which we are now going to review. So if we have a lattice in the complex plane generated by fundamental periods omega 1 and omega 2 with non-real ratio, so we can denote the lattice by lambda, and we know that one of the very simplest ways of constructing an elliptic function with double periods at omega 1 and omega 2 is by constructing the Weierstrass P function. And the derivative of the Weierstrass function, we recall, has three simple zeros in each fundamental parallelogram, and they are exactly omega 1. These are the half periods. Omega 1 over 2, omega 2 over 2, and omega 1 plus omega 2 over 2. And in fact, the Weierstrass P function satisfies this differential equation, which is going to be important in a moment, although we are going to rewrite it in another form. And we recall that the Weierstrass P function has a Laurent expansion about the origin, which can be expressed in terms of Eisenstein series. So that's the Eisenstein series for periods omega 1 and omega 2 as a sum over the lattice points. And we know that we require n to be greater than or equal to 2 for absolute convergence, which means that e of 2 is not defined at the moment, although we can find a way to define it, as we will see later. And e of 2 is important. So what we note at the moment is that the Eisenstein series of order 2n is homogeneous of degree minus 2n, which is very easy to see. And this fact is going to be important in our construction of J. So here's the differential equation satisfied by the Weierstrass P function, but we have rewritten it in terms of Eisenstein series. So Eisenstein series E4 and E6, which are in a sense, they are the most important Eisenstein series if we don't count E of 2, because the other Eisenstein series can be expressed as linear combination of E of 4 and E of 6 with rational coefficients, but we are not going to look at that in this presentation. So one thing which is extremely important is that, as we have noted before, the derivative of P has three simple zeros, and this makes the cubic on the right have a non-zero discriminant. So this expression is read, it's the discriminant of the cubic polynomial, and it is non-zero no matter how we choose our lattice, where omega 1 and omega 2 have non-real ratio. How we are going to use this fact is because when something is non-zero, we can divide by it. And indeed, so we have seen that the Eisenstein series are homogeneous functions. So E4 is homogeneous of degree 4. So E4 cubed is homogeneous of degree 6, of degree 12, sorry. And the denominator is also homogeneous of degree 12, which makes the quotient, and we can divide by the denominator because the denominator is non-zero. This means that this expression on the screen is homogeneous of degree 0, and that's why it's natural to construct this fraction on the screen. And since it is homogeneous of degree 0, we can scale our lattice so that one of our periods is 1 and we denote the other by 2. And we can consider the resulting fraction as a function of only 2, of only one variable. So this thing on the screen here is essentially the j function, as we will see, up to some fudge factor, some constant fudge factor. So it turns out that if tau is in the upper half plane, then the Eisenstein series have particularly nice expressions as series, with coefficients being the sums of divisors function. And we are going to replace these evaluations in this function which we have constructed. And this, when you simplify all the terms, this expression becomes equal to this thing on the screen. And it turns out that this denominator has an extremely nice and very important simplification in terms of an infinite product like this. And we are going to prove this in a while, I mean, assuming a very simple lemma. But the j function is defined as this thing that we have constructed times 1728. I mean, this thing that times 1728 times 60 cubed. That's the j function. Therefore, because when you replace the product in the denominator here, it becomes exactly what we said the j function was before. And we are going now to show this thing that the denominator evaluates to this infinite product. And the way that this is done usually is involves the Dedekind eta function, and the proofs make use of complex analysis and so on. But it is actually possible to show this result making use of only elementary methods, and this relies on a very simple lemma due to Ramanujan, which concerns the derivatives of the Eisenstein series E4 and E6. And so these derivatives are on the screen are being expressed in terms of the Eisenstein series E2, E4, and E6. So we have not defined E2 so far, but E2 is defined as pi squared over 3 times this first factor in the term on the right of the lemma. So E2 of tau is equal to pi squared over 3 times 1 minus 24 times this sum of sigma times q to the r. And this lemma can be proved by purely elementary means, as Ramanujan has shown, using only the basic thing is a very simple trigonometric identity. But we are going to just use the lemma in this presentation to prove the theorem. So the thing basically goes by logarithmic differentiation. It's extremely easy to justify the logarithmic differentiation, so we won't do this in the presentation, but if you differentiate logarithmically the denominator, by straightforward calculation, you get this expression, and the terms in blue can be replaced by the previous lemma. So that's the previous lemma. And when you substitute the lemma in this term, you get basically the second Eisenstein series up to the factor of pi squared over 3. And you can rearrange this as a Lambert series. That's very easy. And this Lambert series is equal to the logarithmic derivative of this infinite product, well, if you multiply everything by q, which would make us have this expression. That's what we want to prove, but we have to show that c is equal to 1728, and that's extremely easy. You just equate coefficients of q on both sides. And this proves the theorem. And what we have done so far is to show that this mysterious j function actually arises very naturally from elliptic function theory. So now that we have seen how the j function arises from elliptic function theory, we still have to talk about the class numbers in binary quadratic form theory. So a binary quadratic form is a function in two variables of this type, and a, b, and c don't have to be integers, but in what we are going to do here, everything will be in integers. So this binary quadratic form, so there are two main most important things with binary quadratic forms. The first is the discriminant, which is defined as b squared minus 4ac. And if it turns out that if d is negative, then f is positive definite. So positive definite means that for whatever integer values you will substitute for x and y, the value of f will be a positive, or rather a non-negative integer, and besides it will be 0 if and only if x and y are both 0. And the second important things with binary quadratic forms is that you can transform them. For example, if you have the binary quadratic form f of x and y, you can replace f of x and y by linear forms in x and y, and you will get a transformed binary quadratic form. And it turns out that if the determinant of this matrix alpha, beta, gamma, delta is equal to plus or minus 1, then f and g are equivalent in the sense that they represent exactly the same integers. And a question which now arises is, given a discriminant d, what is the number of equivalence classes for the binary quadratic forms? And we are almost able to define the class number, but first we make another definition. If a, b, and c are coprime, then f is said to be a primitive binary quadratic form. And now we can define the class number. So the class number is the number of primitive positive definite binary quadratic forms of some negative discriminant d, and it is denoted by h of d. So the class number is a property of the discriminant. And there is a very nice surprising theorem between binary quadratic forms and the J function. So if f of x and y equals ax squared plus bxy plus cy squared is primitive positive definite with discriminant d, which is necessarily negative because it's positive definite, then j of minus b plus the square root of d over 2a is an algebraic integer of degree h of d. And we recall what algebraic integer means. So algebraic means that it satisfies a polynomial equation in integer coefficients. The degree of the algebraic number is the degree of the smallest degree of the polynomial which the algebraic number satisfies. An algebraic integer means that the polynomial is monic, meaning that the coefficient of the highest degree term is 1. So that is indeed a very remarkable theorem. And it makes us all the more want to consider what happens, well, not what happens, but when h of d is equal to 1, because then j of minus b plus square root of d over 2a will be an actual integer, because an algebraic integer of degree 1 is just an integer. And this, it turns out that for negative discriminants, the class number is 1 for only finitely many values. And this is a theorem of Baker-Stark-Heegner, as we said before. It was first conjectured by Gauss, and Gauss had in fact already conjectured all the values, but it was only first proved by Heegner.